Now in this lecture we will find out the size of line segment AE. In the drawing we have quadrilateral ABCD. We know that EB equals to 2 units and line segment DE equals to 8 units, and we also know that this angle DEB is a right angle, it equals to 90 degrees, and we want to find out the size of line segment AE. So we want to find out the size of this line segment AE, the line in the red color. So first of all we will join together points B and D by a straight line. And actually triangle EBD, this triangle is a right triangle, so I write it down. Triangle EBD is a right triangle. So we can implement the Pythagoras theorem on the right triangle, triangle AEBD. Okay, so according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse on the right triangle, triangle EBD, is dB square. dB is the hypotenuse, so the square of the hypotenuse is dB square, and dB square will be equal to EB square plus DE square. So I will repeat again. In this right triangle EBD, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, dB square equals to EB square plus DE square. So dB square equals to EB square. EB equals to 2, so EB square is 2 square, 2 square is 4, plus DE square. DE equals to 8 units, so DE square is 8 square, and 8 square is 64. So in total we got that dB square equals to 4 plus 64. 4 plus 64 is 68. So we found out that dB square equals to 68. Here we will take a root out of equation number 1, and we will get that dB equals to the square root of 68. We found out that dB equals to the square root of 68. So we can write here that dB equals to the square root of 68. Okay, and we also know that all the angles inside a square are right angles, therefore angle BCD is a right angle, it equals to 90 degrees, and also angle BAD, this angle is a right angle and it equals to 90 degrees. Okay? And also, I will present to you rule number 1. According to rule number 1, the diagonals of a square bisect or cross the angles of the square into 45 degrees angles. I will repeat again on rule number 2. Rule number 1. Rule number 1 states that the diagonals of a square bisect the angles of the square into 45 degrees angles. So actually, line segment BD is the diagonal of square ABCD, and therefore, according to rule number 1, this diagonal BD bisect the angles of the square into 45 degrees. That is to say, this angle will be equal to 45 degrees, and this angle is also will be equal to 45 degrees, because of the fact that we know that all the angles inside the square are right angles, and the diagonal bisect the angles of the square. That is to say, it divides the angle that is 90 degrees into two equal angles. That is to say, it divides the angle of 90 degrees into two 45 degrees. So this angle will be equal to 45 degrees, and this angle also will be equal to 45 degrees. So this angle equals to 45 degrees, and the other half of the angle, this angle will be also equal to 45 degrees. And we will define side DC of quadrilateral ABCD as Y, and the triangle DCB is a right triangle. Triangle DCB is a right triangle. And in the right triangle DCB, this right triangle, we know that cosinus 45 degrees equals to DC over DB. DC over DB. I will repeat again. In the right triangle BDC, cosinus 45 degrees equals to DC over DB. But DC equals to Y according to our definition, and DB equals to square root of 68. Okay, so in total we got that cosinus 45 degrees equals to Y over square root of 68. But we know that cosinus 45 degrees equals to the square root of 2 over 2. So the square root of 2 over 2 equals to Y over square root of 68. So here we will multiply equation number 2 by square root of 68, and we will get that square root of 2 over 2 times square root of 68 equals to y. Okay, square root of 2 over 2 times square root of 68 equals to y. We know that 68 is 34 times 2, so we write it down. So square root of 2 over 2 times 68 is 34 times 2, and it equals to y. And we also know that the square root of a times b equals to the square root of a times the square root of b. Okay, so according to this rule, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2. And it is multiplied by square root of 2 over 2. This is equation number 2. And it equals to y. Okay, so here square root of 2 times square root of 2 is 2. So 2 over 2 times square root of 34 equals to y. 2 over 2 is 1, so 2 will get cancelled. So we actually found out that y equals to the square root of 34 units. Okay, we found out that y equals to square root of 34 units. So we can write here that y equals to the square root of 34 units, and because of the fact that all the sides of a square are equal to each other, therefore side BC of square ABCD will be also equal to the square root of 34, and side AB of square ABCD will be also equal to the square root of 34, and side AD of square ABCD will be also equal to the square root of 34. Okay? So, as you can see from the drawing, we found out all the line segments in this drawing, and the only missing line segment is line segment AE. Okay, I will present to you rule number 2. According to rule number 2, if a line segment AB subtends two equal angles, then the square ABCD, the quadrilateral ABCD, is inscribed by a circle and the 4 points A, B, C, and D lie on that circle. I will read rule number 2 again. Rule number 2 states that if a line segment AB subtends two equal angles, then the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So, what is the meaning of rule number 2? The meaning of rule number 2 is that if we have line segment AB, suppose that we have only line segment AB without this circle, but only line segment AB. So this think that this circle doesn't exist at all, but only line segment AB. So if we have line segment AB, and on line segment AB we have two equal angles that subtend on line segment AB. So the first angle that subtends on line segment AB is angle theta. So angle ACB equals to theta, and angle ACB subtend or rest on line segment AB, and we also have the second angle that also subtend on the same line segment AB. Okay, suppose that the circle doesn't exist at all, but only we have line segment AB and those two angles that are both equal to theta, and both of them subtend on the same line segment AB. Again, we have only, the circle doesn't exist at all, but we have only the line segment AB and those two equal angles, they are both equal to theta, and they subtend on the same line segment AB. Then according to rule number 2, so if this is the reality, that we have two equal angles that subtend on the same line segment from the same side, then according to rule number 2, the quadrilateral ABCD, this quadrilateral ABCD is inscribed by a circle. So suppose that we draw the circle now. So only if we know that we have two equal angles that subtend on the same line segment AB, then we can conclude from it that the quadrilateral ABCD is inscribed by a circle. Only after we know that two equal angles subtend on the same line segment, only then we can conclude that the quadrilateral ABCD is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. Okay, so actually this is the meaning of rule number 2. I'll repeat again. if we have only the line segment AB and the two equal angles that subtend on the same line segment AB without this angle at all. We have only line segment AB and those two angles, equal angles that subtend on the same line segment AB from the same side. Then, according to rule number 2, the quadrilateral ABCD is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. Okay, so this is the meaning of rule number 2, and we actually can implement rule number 2 in our drawing, because in our drawing we have those two right angles that subtend on the same line segment DB. Again, those two right angles, angle DEB and angle DEB is a right angle. It is subtend on line segment DB, and we have also angle BAD that is a right angle and subtend on the same line segment DB. So I will write it down. We have angle DEB that equals to 90 degrees. Angle, it is given us in the question that angle DEB or BED, it is the same. Angle BED is a right angle, it equals to 90 degrees, and angle BED subtend on line segment BD. Okay? I will repeat again. Angle BED equals to 90 degrees, and this angle subtend on line segment BD, this line segment, and we also have the second angle, angle BAD equals also to 90 degrees. Angle BAD equals also to 90 degrees, and it is also subtend on line segment BD. I repeat again. Angle BAD, this angle is also equal to 90 degrees, and it is also subtend on line segment BD. So we actually have two equal angles. They are both equal to 90 degrees, and they are both subtend on the same line segment from the same side. So according to rule number 2, the quadrilateral AEBD, so we can conclude from it that according to rule number 2, the quadrilateral AEBD is inscribed by a circle, so the quadrilateral AEBD in the green color, the quadrilateral that I paint in the green color is inscribed by a circle. The quadrilateral in the green color AEBD is inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. And the 4 points A, E, B, and D lie on that circle. Okay? I will repeat again. Because of the fact that we have two equal angles, two right angles that subtend on the same line segment BD, then according to rule number 2, the quadrilateral AEBD in the green color is inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. So according to rule number 2, we have quadrilateral AEBD that it is inscribed by this circle. So here we have quadrilateral AEBD, quadrilateral AEBD in the green color is inscribed by a circle, again quadrilateral A, E, B, D. This quadrilateral is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay? So I will also paint quadrilateral AEBD in the green color, exactly like in this drawing, in order to emphasize that it's the same quadrilateral AEBD in the green color. And I will also repeat on rule number 2, according to rule number 2, because of the fact that this right angle EAC, angle BAD, so it is AEBD, so it is actually angle BAD is a right angle. So actually angle BAD is a right angle. So actually this angle is a right angle, angle BAD. This angle BAD is a right angle, so this angle also angle BAD is a right angle, and also angle BED is also a right angle, equals to 90 degrees. So because of the fact that we have two right angles that subtend on the same line segment BD, therefore according to rule number 2, the quadrilateral in the green color is described by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, that is actually the implementation of rule number 2 in our drawing. Okay, again, this quadrilateral in the green color is described by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, and so I'll repeat again, we have two equal angles, they are both right angles that subtend on the same line segment BD. Therefore, according to rule number 2, the quadrilateral in the green color, quadrilateral AEBD, is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. That is according to rule number 2. Or actually, that is the implementation of rule number 2 in our drawing. Okay? And we actually also have rule number 3. According to rule number 3, before that, I will repeat again that we got this drawing. This drawing is true according to rule number 2. So we have our quadrilateral AEBD that is in the green color. It is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, so we also have rule number 3. According to rule number 3, if quadrilateral ABCD is inscribed by a circle, if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. I will repeat again. According to rule number 3, if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So what is the meaning of rule number 3? The meaning of rule number 3 is that if we have quadrilateral ABCD that is inscribed in this circle, so this quadrilateral in the red color, quadrilateral ABCD, is inscribed by this blue circle, and we also know that side AB of quadrilateral ABCD equals to A units in its size, side BC of quadrilateral ABCD equals to B units in its size, and side CD of quadrilateral ABCD equals to C units in its size, and side AD of quadrilateral ABCD equals to D units in its size. Then and we also know that quadrilateral ABCD has two diagonals. The first diagonal is diagonal AC, and the size of diagonal AC is x, it equals to x units in its size, and quadrilateral ABCD also has second diagonal, diagonal DB, and diagonal DB equals to y units in its size. So if we have quadrilateral ABCD that is inscribed by this blue circle, then according to rule number 3, the product of its diagonals, that is to say x times y, equals to the sum of the products of its opposite sides. So quadrilateral ABCD has two pairs of opposite sides. The first pair of opposite sides is actually side AD is opposite to side BC. Side AD equals to D units in its size, and side BC equals to B units in its size. So the product of the first opposite sides, it is actually B times D. And quadrilateral ABCD has also second pair of opposite sides. The second pair of opposite sides, it is actually side AB is opposite to side CD, and AB equals to A units in its size, and CD equals to C units in its size, and the product of the second pair of opposite sides, it is actually A times C. Okay, so we have two products of the opposite sides. The first product is B times D, and the second product of the opposite sides is A times C. And the sum of the products of its opposite sides, it is actually BD plus AC. And that sum of the products of its opposite sides equals to the products of its diagonals, that is actually x times y, or the products of its diagonals, that is actually x times y, equals to the sum of the products of its opposite sides, that is actually BD plus AC. Okay, this is rule number 3, and we also implement rule number 3 in our drawing. We arrive to the conclusion that this green quadrilateral AEBD is inscribed by a circle, and the 4 points AEBD lie on that blue circle according to rule number 2. So we actually arrived to this drawing according to rule number 2. Because of the fact that we have two right angles that subtend on the same line segment BD, therefore according to rule number 2, the green quadrilateral AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. So this drawing is true according to rule number 2. Now we will implement rule number 3 in our drawing, because rule number 3 is true for any quadrilateral that is inscribed in circle by a circle, and the green quadrilateral AEBD is indeed inscribed by this blue circle. Therefore we can implement rule number 3 in this drawing. And according to rule number 3, because of the fact that we have quadrilateral AEBD that is inscribed by this blue circle, then according to rule number 3, the product of its diagonals, that is to say AB times ED, AB times ED, equals to the sum of the products of its opposite sides. And actually quadrilateral AEBD has two opposite sides, and the first product of its opposite sides, it is actually AE times BD. That is the first product of its opposite sides. And the second product of its opposite sides, it is actually AD times BE. And the sum of the products of its opposite sides is product number 1 plus product number 2. So the sum of the product of its opposite sides, that is to say AE times BD plus AD times BE, equals to the product of its diagonals, that is actually AB times DE. This equality number 3 is true according to rule number 3, or actually the implementation of rule number 3 in our drawing gives us equation number 3. Okay? Or equation number 3 is the implementation of rule number 3 in our drawing. The product of its diagonals the product of a quadrilateral that is inscribed by a circle, the product of its diagonals, it is actually AB times DE, and it equals to the sum of the products of its opposite sides, that is actually AE times BD plus AD times EB plus AD times EB. Okay, this equation number 3 is the implementation of rule number 3 in our drawing. Okay, so what is the size of AB? The size of AB, if we look at in our original drawing, the size of AB is square root of 34. Okay, so the size of AB is square root of 34. What is the size of DE? The size of DE is 8 units. It is given us in the question. So DE or ED, it is the same, equals to 8 units according to what is given as the question, and it equals to AE. AE is the missing line segment that we are looking for, so we will leave it as it is, times BD. What is the size of BD? The size of BD, we've already found out that the size of BD is square root of 68. Again, AE is AE, and DB equals to square root of 68. And what is the size of AD? The size of AD equals to square root of 34. Again, the size of AD equals to square root of 34. And what is the size of BE? The size of BE equals to 2 units. It is given us in the question. Okay, so the size of AD equals to square root of 34, and the size of BE equals to 2 units. It is given us the question. So we have only one variable that is missing, that is line segment AE, that is the line segment that we are looking for. So here we know that 68 is 34 times 2, so we write it down. 68 equals to 34 times 2. So we substitute 68 by 34 times 2, and we will get that 68 is 34 times 2 plus square root of 34 times 2. And according to the rule that the square root of AB is square root A times square root B, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2. So I write it down. So here we will divide equation number 3 by square root of 34. So here square root of 34 will get cancelled. And what is left after we cancel square root of 34? What is left is actually 8 equals to square root of 2 times AE. AE is the missing line segment that we are looking for, plus 2. So here we will subtract 2 from this equation number 3, and we will get that 8 times 8 minus 2 is 6. So 6 equals to AE times square root of 2. So here we will divide the equation number 3, this equation, by square root of 2, and we will get that AE equals to 6 over square root of 2. So we found out that AE equals to 6 over square root of 2 units. 6 is 3 times 2, so I write it down. AE will be equal to 3 times 2 over square root of 2. So here we will multiply this expression by square root of 2, and then we will divide it by square root of 2, and we will get that AE equals to 3 times 2 times square root of 2 over square root of 2 times square root of 2. So here in the denominator we have square root of 2 times square root of 2 is 2. So in total we will get that AE equals to 3 times 2 times square root of 2 over square root of 2 times square root of 2 is 2. And here 2 over 2 is 1, so 2 will get cancelled. And we found out that line segment AE equals to 3 times square root of 2 units, or in terms of numbers, line segment AE equals to 4.243 units. So I will repeat on the question, on the answer again. The answer to the question is that line segment AE, this line segment, equals to either 3 times root 2 units, or in terms of numbers, line segment AE equals to 4.243 units. Okay, that is the answer to the question. Now I will summarize the lecture. Actually, we wanted to find out the value of line segment AE, or the size of line segment AE, and we know that we have a square ABCD. EB equals to 2 units, DE equals to 8 units, and angle BED, this angle is a right angle, and we want to find out the size of line segment AE. Okay? So the first thing that we did here is we connected together points B, we joined together points B and D by a straight line, and then actually triangle BED is a right angle because of the fact that this angle equals to 90 degrees, therefore triangle BED is a right angle. So we can implement the Pythagoras theorem in the right triangle, triangle BED. And in the right triangle BED, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay? That is to say, dB square equals to EB square plus DE square. Okay? So dB square equals to EB square. EB equals to 2 units, so EB square is 2 square, 2 square is 4, plus DE square. DE equals to 8 units, and DE square is 8 square, 8 square is 64. So dB square, according to equation number 1, equals to 4 plus 64 is 68. So we got that dB square equals to 68. We took a root out of equation number 1, and we found out that the size of BD is actually square root of 68 units. So we found out that the diagonal dB of square ABCD equals to square root of 68 units. Okay, then we have I presented to you rule number 1. According to rule number 1, the diagonals of a square bisect the angles of the square into 45 degrees angles. So we have here diagonal DB. Diagonal DB is the diagonal of square ABCD, and according to rule number 1, the diagonal DB bisect the angles of square ABCD into 45 degrees. That is to say, this angle equals to 45 degrees, and this angle also equals to 45 degrees. Likewise, this angle will be also equal to 45 degrees, and this angle will be also equal to 45 degrees because of the fact that the diagonal DB bisects the angles. What is bisect? It divides it to two equal parts, or to two equal angles. So this angle will be equal to 45 degrees, and this angle will be also equal to 45 degrees. Likewise, this angle will be equal to 45 degrees, and this angle will be also equal to 45 degrees because of the fact that all the angles inside the square are right angles. And it bisects this, so it means that it divides the angle into two equal angles, to 45 degrees and 45 degrees. Okay, so according to rule number 1, this angle is 45 degrees and this angle is also 45 degrees. And we know that all the angles inside the square are right angles, so this angle is a right angle BCD is a right angle, so triangle BCD is a right angle because it has one angle that equals to 90 degrees. So in the right triangle BCD, this right angle, cosinus 45 degrees equals to DC over DB. In the right triangle DCB, cosinus 45 degrees equals to DC over DB. We defined DC as Y, so DC equals to Y, and DB equals to square root of 68 units. We have already found out that DB equals to square root of 68. So actually cosinus 45 degrees equals to DC, that is Y, and DB that equals to square root of 68. And we know that cosinus 45 degrees equals to square root 2 over 2, and all equals to Y over square root of 68. Here we multiply the equation number 2 by square root of 68, and we got that Y equals to square root of 2 over 2 times square root of 68. But we know that 68 is equals to 34 times 2. So we substituted 68 by 34 times 2. And we have the rule that the square root of AB equals to the square root of A times square root of B. So according to this rule, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2. Okay, so we have here this equality, because square root of 34 times 2 equals to square root of 34 times square root of 2, and it equals to Y. So here we have square root of 2 times square root of 2 is 2. So we got here 2 times square root of 34 equals to Y, and all divided by 2. 2 over 2 is 1, so 2 will get cancelled, and we got that the size of Y, the size of one side of a square equals to square root of 34 units. So Y equals to the square root of 34 units, and all the sides of a square are equal to each other, so PC also equals to the square root of 34, AB also equals to square root of 34, and AD also equals to the square root, AD also equals to the square root of 34 units. And then I presented to you rule number 2. According to rule number 2, if a line segment AB subtends two equal angles, so we have, suppose that the angle doesn't exist at all and we have only line segment AB, and this line segment subtends two equal angles. Those two angles are both equal to theta and they subtend on the same line segment AB. So if this is the reality, then according to rule number 2, the quadrilateral ABCD is described by a circle, and the 4 points A, B, C, and D lie on that circle. So because of the fact that we have two equal angles that subtend on the same segment line AB from the same side, Then according to rule number 2, the quadrilateral ABCD is inscribed by this blue circle, and the 4 points A, B, C, and D lie on this blue circle. This is the implementation of rule number 2 in our drawing. Actually, we implemented this is rule number 2, and we implemented rule number 2 in our drawing. Actually, we have here two equal angles that subtend on the same segment line BD. Angle BED that equals to 90 degrees subtend on line segment BD, and angle BAD that also equals to 90 degrees subtend on the same segment line BD. Therefore, according to rule number 2, the quadrilateral AEBD is inscribed by a circle, and the 4 points A, E, B, and D lie on this blue circle. Okay? So, again, the quadrilateral in the green color AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Why? Because according to rule number 2, we have two right angles that subtend on the same segment line BD. Therefore, according to rule number 2, the green quadrilateral AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, so we arrive to this drawing by implementation of rule number 2 in our drawing. Okay, so we have a quadrilateral AEBD in our original drawing that is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, and then we also implemented rule number 3 in our drawing. According to rule number 3, if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So we have this quadrilateral ABCD in the red color that is inscribed by this blue circle. Okay, whenever we have quadrilateral that is inscribed by a circle, we can implement rule number 3. And what is the meaning of rule number 3? According to rule number 3, whenever we have a quadrilateral that is inscribed by a circle, then the product of its diagonals, that is to say x times y, equals to the sum of the products of its opposite sides, equals to the sum of the products of its opposite sides. The first product of its opposite sides is BD, and the second product of its opposite sides is AC, and the sum of the products of its opposite sides is BD plus AC. And that sum of the product of its opposite side, that is BD plus AC, equals to the product of its diagonals, that is actually x times y, or the product of its diagonals, that is x times y, equals to the sum of the products of its opposite sides, that is actually BD plus AC, because the first product is BD of its opposite sides, and the second product is AC. And the sum of the product of its opposite sides is the first product, that is BD, plus the second product, that is AC. And that product equals to the product of its diagonals, that is actually x times y. So we implemented rule number 3 in our drawing. In our drawing, we have a circle that is inscribed, actually quadrilateral AEBD is inscribed by this blue circle, because we implemented rule number 2 in our drawing, and we got to the conclusion that this green quadrilateral is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Now we will implement, so because of the fact that we have quadrilateral that is inscribed by a circle, we can implement rule number 3 in our drawing. Any quadrilateral that is inscribed by a circle, like in this drawing, we can implement Rule number 3 in that drawing. We have here quadrilateral that is described by Sigurd, therefore we can implement rule number 3 in this drawing. And according to rule number 3, the product of its diagonals, that is to say AB times ED, AB times ED is the product of quadrilateral AEBD diagonals, equals to the sum of the products of its opposite sides. And the first product of its opposite sides, it is AE times BD, AE times BD, and the second product of its opposite sides is AD times EB, AD times EB, and the sum of the products of its opposite sides is product number 1 plus product number 2. That is the sum of the product of its opposite sides equals to the sum of the products of its diagonals, that is actually AB times ED. So actually equation number 3 is the implementation of rule number 3 in our drawing. Okay, equation number 3 is the implementation of rule number 3 in our drawing. Okay, and then we know that AB equals to square root of 34, DE equals to 8 units, AE is the missing line segment that we are looking for, so we will leave it as it is. DB equals to square root of 68, AD equals to square root of 34, and BE equals to 2 units. According to what is given us in the question, BE equals to 2 units. Okay, so, and we also know that 68 is 34 times 2, so we'll substitute 68 by 34 times 2, and we got this equality. 68 is 34 times 2, and we have the rule that the square root of a times b equals to the square root of a times square root of b. Therefore, according to that rule, the square root of 34 times 2 equals to the square root of 34 times square root of 2. Okay, the square root of 34 times 2 equals to the square root of 34 times square root of 2. So we got this equality, and we divided equation number 3 by square root of 34. So square root of 34 cancelled from this equation number 3, and what is left after we cancelled square root of 34, what is left is 8 equals to square root of 2 times AE plus 2. We subtracted 2 from equation number 3, and we got that 6 equals to AE times square root of 2. Then we divided equation number 3 by square root of 2, and we got that AE equals to 6 over square root of 2. But we know that 6 equals to 3 times 2, and here we multiplied this expression by square root of 2, and then we divide it by square root of 2, so we change nothing. And here in the denominator, square root of 2 times square root of 2 is 2. Okay, and we have here 2 over 2 is 1, so 2 will get cancelled, and what is left is that the size of line segment AE equals to 3 times square root of 2 units, or in terms of numbers, the size of line segment AE equals to 4 times 2 for 3 units. I will repeat again, the size of line segment AE, this line segment equals to either 3 times root 2 units, or in terms of numbers, the size of this line segment AE equals to 4.243 units. Okay, thank you very much.